Hello everyone. In this lecture we're going to start discussing unsupervised learning techniques so that you can train massive or large neural network without having to have necessarily all labeled data. One key concept of unsupervised learning and what distinguishes it from supervised is that even in real life, many times we don't get a lot of examples or continuous examples of what we have to learn. We just, as humans, we are able to learn from sometimes a single presentation after we are old enough to have our system well initialized. Even little babies can understand and learn a new object just out of a single presentation. In reality, it's never a single presentation, because really when somebody presents you an object or shows you a dog, you see a sequence of, say, images, or you see a sequence of frames, or a sequence of perception, of visual perception. So it's never really just one object, but we are able to learn it. So there must be techniques that allow you to generalize and create a system that can learn fairly quickly. Another big interest in unsupervised learning is that labeled data is extremely expensive, especially in terms of labeling videos or large quantity of images. And one would want to have as little label as possible and try to have a system that learns by itself without all this. Okay, without spoiling further the rest of the lecture, we'll go into the slides and slowly see all of these details. So we've been discussing together for a while deep networks, deep architecture of neural networks. In particular, we learned about convolutional neural networks. So let's keep that in mind, even though we discussed it in the context of supervised learning in the last lectures or two. We here will discuss the same topic in terms of unsupervised. So remember, deep network is basically composed of multiple layers of processing, layer 1, layer 2, layer 3, before you get to a classifier, if any, that will tell you what's in the image. The input image, again, can be one single image, an image in color, so 3 planes, a stereo image, so 3 planes for each of the 2 images, or it could be a video, so n frames of 3 planes, for example, if it's in color, or it could be a stereo video, so it could be 6 images on each side, three images left and right for every frame that you want to process. So here you could have multiple inputs. And then just to remind you, one layer is composed of multiple operations. You have a convolution with some filters, subsampling, and nonlinearity. So we'll keep this architecture also for unsupervised learning, and let's see how this is not really going to be affected. Really, the main thing that supervised and unsupervised differ is how do you get these filters. So the mass of really parameters in a convolutional neural network or a deep network is really at this level here between the input. It could be input image, or it could be many features from the previous layer, and you have to go to features on another layer. So the mass of really parameters is one, what filter you use to convolve the input image or images to get the output images, and 2 is this connection table. So how do you combine together multiple maps so that to generate a map in the next layer. The rest is more or less the same, although it could be changed if subsampling doesn't change, nonlinearity doesn't change. So really the question is, how do we compute these filters? We've seen how you can do it supervised by basically propagating the error with stochastic gradient descent from the output to the input. So supervised training basically uses a large data set that is usually labeled. So, you know, it's labeled like this is a woman, this is somebody jumping, there's a horse, another horse, and so forth. So this is drinking, action. All of these images could be labeled, and then you use stochastic gradient descent to basically backpropagate the error until you find really the local minimal of the network that tells you how it should be organized. So in terms of deep network, we've seen in the previous lecture that that means that in order to generate these filters, not the connection matrix, that's another issue, but in order to generate these filters, you minimize some kind of a cost function. Don't worry about this specific formula, it's just an example, but you try to minimize a cost function that basically reduces the error between the input and the reconstructed output, and also tries to minimize, make these filters as sparse as possible, not with large values. It doesn't really matter what kind of function you use, you just do gradient descent to minimize this. So supervised training has some problems, some issues that I'm going to discuss here. So, you know, the biggest issue is that you need labeled data. So that means it takes a very long time and you need some human person to label all the data. Lots of effort. In video, I say it is crazy because for every minute of video, you have to label 33,000 images, 36,000 images if you're at 30 frames per second, or less if you're less frames, but it's too much. We cannot really scale this up. I mean, we cannot just take video, you know, humans that are now producing videos on YouTube at an enormous rate. We cannot scale this thing up because we just don't have enough humans that can label all of this. For every minute of video, it might take you half an hour to an hour to label things. So, I mean, really, this is the task that you want a computer to do, labeling for you, or bootstrapping labeling for you. I'm surprised that still a lot of the work is done on supervised training and improving small techniques rather than trying to get rid of labeled data almost altogether and scale to other. So this is the purpose of this lecture, really, to explore this. So all of the supervised training also uses gradient descent, which is, first of all, one of the comments that is usually done is it's not related to learning in the brain. Uses a global error propagation, which is probably not a very bio-inspired technique. Usually we think that at least the brain learns by local error propagation, not global error propagation. You might think that this is not a big deal. Why do we have to copy human brain if we can get machines that are better? But obviously, up to now, we cannot do that. We do not have machines that are better than humans. It makes sense then to think again about learning techniques that we're using and see if there's a possibility of improving them. These techniques, also these gradient descent techniques, are also very math-heavy technique, which means it takes a long time to compute, maybe weeks, and some people don't really want to spend that much time.